when you want to anti-differentiate an exponential, more specifically something with the base of e, then you can use this rule above here. If the base is not equal to e, you cannot use this. So remember that we do need to have the base of e. Okay. Anyway, so when you want to take the antiderivative, normally when you take the derivative, you would put this k value, the coefficient of x, to the front, because what you're doing is you're doing the chain rule, and you're taking the derivative of your index and putting it to the front. So this time, we take the antiderivative. This k over here is going to be what you divide by. So you have 1 on k instead. And the plus c over here is just the constant that you have when you take the indefinite integral. So let's begin by going through a couple of examples. So 2e to the 4x, you want to integrate this. So in this case, then what you end up with is 2. So I'm going to take this 2 to the front first, multiplied by, what's k over here? K is just the number in front of x. So we have 1 on 4, e to the power of 4x. So note that how over here, the index is always going to stay the same whenever you anti-differentiate or differentiate. So this is the simple part. The only difficult part is knowing what to put in front. When you anti-differentiate, you just do 1 divided by the coefficient of x here, and plus c, just to finish off. Over here, 2 times 1/4 is just half, e to the 4x plus c. Alright, pretty simple. Okay, for this one over here, things get a little bit dicey. So, a couple of ways you can interpret this one. Now, other than the negative index here, which actually isn't too much of an obstacle, is this 2x plus 3 over here. We only dealt with kx, so just the 2x term. But what happens when there's a plus 3 here? Just note to yourself that for this term over here, e to the 2x plus 3 is the same as saying e to the power of 3 multiplied by e to the 2x. Because remember that with your index laws, that if you multiply 2 terms with the same base, that the indices simply get added to each other. So you can actually just separate it into 2 different terms if you want, and just multiply by each other. And you can treat this one over here as a constant. If you have a constant in front, of course, you can really just leave this out to the very end and just anti-differentiate e to the 2x instead. So that's what we're going to be doing. So integrating this whole thing, you have 5 times 1 on k, k is negative 2. E to the power of negative 2x, that remains the same, plus, okay, so we're going to interpret this as e to the 3 multiplied by e to the 2x. So e to the 3 is a constant, multiplied by 1 on 2, e to the 2x plus c. Okay, so what we end up with here is negative 5 on 2. E to the negative 2x. And over here, you'll find that it actually doesn't really matter if you separate this e to the 3 from this term over here. Sorry, it doesn't matter if you separate e to the 3 from e to the power of 2x plus 3. You notice how these two are still multiplied by each other. You can still add these two indices together because you're still multiplying all 3 of these together, e to the 3, half, and e to the 2x. So we still end up with half times e to the 2x plus 3 plus c. So what did we learn here? Well, you can't separate it out and just treat the plus 3 here, or whatever constant that you have in your index, and put it to the front. But in the end, it doesn't really matter if you separate it or not. You just take the value of the coefficient of x, chuck it in front. So what I'm talking about here is this 2 over here gets put to the front, and of course you're dividing it at the front. And this plus 3 here, you can just leave it there if you want. Doesn't really matter. And you just anti-differentiate it as if you're just leaving this index here intact, and you're just dividing by the value of k, the coefficient of x inside the coefficient. Okay, so last one, of course, try this out before we attempt it together, because it does make use of all of the skills that we just used. So pause it if you want to attempt it, otherwise let's go through it. So over here, 6 multiplied by 1 on k, k is 3 in this case, e to the 3x. Over here we have 4 multiplied by 1 on negative 2, e to the power of 7 minus 2x. So remember, the 7 over here doesn't really matter. You can take e to the 7 to the front, but we're only interested in the coefficient of x, which is negative 2. That's why it's over here. And I think I may run out of room, so I'm just going to put the last term down here. So plus 10 and divided by 1 on negative 5, e to the power of negative 5x, plus c. Okay, so this one over here becomes 2, e to the 3x. Next term is 4 times negative half, so let me just get rid of that positive, it's now negative. So we have 2, negative 2 times e to the power of 7 minus 2x. Over here, 10 times negative 1/5. Oh, not a 2. And e to the power of negative 5x plus c. Of course, you can factorize 2 right to the front and make your constant over here c1 and say that you have a factor of 2 being taken out, but it's really optional. It's up to you. But if you do want to factorize it out, you can say it's this instead. Taking 2 from each of the e terms. And say that we're going to be adding by a different constant, c2, where of course c2 is just half of c1 since we divided everything by 2. Actually, no, never mind. Still c1, because we only divided the first 3 terms by 2. Okay, so no, actually, this constant will actually stay the same. So no biggie there. And yeah, that wraps it up. So just make sure that the index is a linear. The index is of linear nature. If it's a quadratic or some sort of other function, maybe a trig function or a logarithm up there, you may need to use a different technique to differentiate.